want to take a little opportunity here to get a start on rotational kinematics and describe how you apply some of this information to some problems in Chapter 7. First of all, let's jump over to our first slide here. Equations of rotational kinematics are really the same as those equations for linear motion that you already know. The equations listed here on the left-hand side, right, are equations we've used many times. So we just need to have a mechanism for converting them to rotational type equations. What we're referring to in the case of rotation is that an object, here let's draw, as best I can, let's draw a little axis here, XY axis. If an object is rotating, well, let's draw a little bar and a mass out here, okay, and this mass is rotating in a circle, right? Then its position X and Y can actually be determined by knowing the radius R from the origin and the angle theta. In fact, the angle theta is the coordinate that measures the location of the object because R is a constant. So instead of using X and Y to locate this object, simply stating R and theta, and if R is constant, then simply stating theta is enough to locate the object. So instead of using the position X to define the location of an object, we'll use the symbol theta. So everywhere you see an X in your kinematics equation, we're just simply going to replace that X, whether it's X by itself or X with a subscript 0 on it. We're going to replace that with a theta and then keep the subscript 0 to indicate it is the original position, right? So here in the first equation we see that X is replaced by theta. Down here in the fourth equation and in the fifth equation. Okay. All right, now let's go to the next step. Since the old definition of V for linear motion was delta x over delta t, remember the definition of velocity, then to take this into a rotational equation, we replace delta x by delta theta. Okay, so this delta theta over delta t is a measure of the rate at which the angle changes. So that's the angular velocity, and we give that the symbol omega. Okay, omega, and that's going to be measured in radians per second as opposed to meters per second. Okay, so down here in our formulas, everywhere we have a V, whether it's V average or V0 or V by itself, we're going to replace that with an omega and keep the subscript average and keep the subscript 0. Okay, and then we're just converting. We're just converting the equations we already know into equations that can apply for rotational motion. Okay, So this is called angular speed or angular velocity in radians per second. All right? Okay. Where's my little... Okay. Now, let's see. We've converted x to theta. We've converted v to omega. All right? We've converted v to omega. So the last thing we need to convert is the acceleration a. Okay, so let's take a. Where is a? Here. We're going to convert that into the symbol alpha. Okay. Alpha. Where can we write that? We'll write that over. We'll write that up here on top. Alpha is the Greek lowercase a, so that's going to be from the definition of acceleration, linear acceleration. We had delta v over delta t was linear acceleration, right? So a, linear acceleration, delta v over delta t. We replace v with omega, right? We replace v with an omega. We've converted our rate of change of linear speed to a rate of change of angular speed, and therefore we have the angular acceleration. Okay, alpha, angular acceleration in radians. Again, that's a measure of the angle. And per second squared, because accelerations are always in per second, which is seconds squared. So there we go. We've got everywhere we see an a in our formulas, here and over here. We can convert that over and put an alpha in our formulas. It's that simple, folks. There's the set of equations that we can use to do rotational kinematics, just like we did linear kinematics back in Chapter 2 and Chapter 3. So let's go ahead and look at an example. Let's see, in this particular case, we have a bicycle wheel, so it's a rotating object. Okay. Not a very good wheel, is it? Okay. Let's see here, maybe a little bit of a hard to see the pen sometimes. Okay. So basically we've got this wheel, okay? And it's turned upside down, and we're rotating at a rate of 60 RPMs. Oh, that's a different unit of measure, like miles per hour instead of meters per second. So the RPM is revolutions per minute, isn't it? Okay. Well, it's an angle per time, so that is an omega quantity, speed, but it's not in the units we're used to. We can convert it. If you go around one revolution, that's going to be 2 pi radians, right? And 60 minutes, a minute is 60 seconds, right? So if you take that 60 RPMs and multiply and divide by 2 pi over 60, you're going to get the radians per second. for our initial speed. Okay. So obviously it's 2 pi, isn't it? Okay, now if the wheel slows uniformly to a stop, so that means this is actually going to be our omega 0, isn't it? Our starting omega. And we know our final omega is 0 because it's going to slow to a stop. And it does that in 15 seconds. So we've got our delta t, 15 seconds. Okay. So that information would enable us to calculate the acceleration. If we wanted to, we could calculate the angular acceleration, couldn't we? From delta omega over delta t. Or as I show here, we also can find the average speed. And with the average speed and the time, we can find the number of radians that it makes during this time. Okay. Now you notice in the problem example up here, I didn't convert the velocity from revolutions per minute because we were asking for how many revolutions does the wheel make during this 15 seconds. We did have to convert the minutes to seconds. That gave us 1 revolution per second. Okay, but let's take a look at what this would look like if we did simply do everything in radians per second. So omega 0, notice the 60 cancels here and the 60 there, so it's in radians per second is 2 pi, right? Okay, so that means that omega average would be omega 0 is 2 pi, omega final is 0, so half, add them together, divide by 2, that means the average angular velocity is just pi radians, radians per second. And if the time is 15 seconds, right, and we apply this formula, theta is omega average t, this is going to give us theta of 15 pi, isn't it? 15 pi. Okay, what's 15 pi? That's my phone, not my calculator. 15 times pi, 15 times pi is 47.1. I just used 3.14. Okay, 47.1 radians. Radians. Okay. Oh, so if the problem wanted revolutions and we did it in radians, then how would we convert to revolutions? Well, up here you saw that 2 pi is the same as a revolution, isn't it? Right? So that means basically 6.28, we jot that over here on the right hand side, 6.28 is 2 pi is equal to 1 rev. Okay, so if we were to divide 47 radians by 6.28, that would convert the 47.1 into the number of revolutions, and we get 7.5 revolutions. Oh, there we go. So we knew that already because it's up here in the answer. Solve the other way. Okay, let's take a look at another problem then. Oops, too far? There it is, okay. A bicycle wheel starts from rest and rolls 150 meters without slipping. Okay, when we have these sorts of conditions, rolls without slipping, that means that the distance traveled by the wheel in a straight line is related to the angle that the wheel turns through as it's rotating times the radius of the wheel. So this is a connecting formula between linear distance on the left and rotational distance on the right. And notice that we have r, okay, and we have x. So we could convert this to a theta type formula. Theta equals 0.2. Okay. 0.2 is 1/5. 5 times 150 is 750. So that would say during in order to travel 150 meters while rolling, the wheel has to turn through 750 radians to do that. Okay, well, let's see if that's number of radians through which it turns. Oh, that's the answer to B, isn't it? There's B. Okay. The number of revolutions. Okay, well, A, because I'm sort of solving this backwards, we can convert 750 radians to revolutions by dividing by the number of radians per revolution. What's that give us? $119.43. Revs. Okay. All right. Now, let's see. What else can we do? Well, notice in part C, I don't know why I wrote part B there. Let's get rid of that. Go back to the pen. Part C, we have the time of 30 seconds. We know the angle theta through which we were turning, 750. So I guess we could use the formula to find the average velocity. Theta equals omega average t. Go ahead and plug that in there and find that omega average is what, 25 radians per second. And oh, that's what we're looking for in C, isn't it? Okay, oh, that's good. So that wasn't too hard, was it? Just kind of make sure you identify what the terms are up here, what each of the numbers means. The fact that it started from rest is not used in this particular case because we only looked for the average angular velocity. What if we wanted to know the final value of omega, right? Final omega. Well, what we know from the fact that it starts at rest is that omega 0 is 0, and omega average is 25. So starting from 0 with an average of 25, that would mean your final omega would have to be 50, wouldn't it? 50 radians per second. Anyway, okay, so a little help there. Hope that helps you start these problems in chapter 7. See you in class.